Good afternoon. I will talk about space research that we do at our Ústav technické experimentální fyziky at ČVUT. First, some short history. So most of our space research is based on the Timepix detector, which was, it's a sensor, pixelated sensor that was developed at CERN for accelerators. And as such can withstand high radiation loads and is good to use in space as well. So our space usage of Timepix started 10 years ago when we deployed 6 Timepix light units on board the International Space Station in collaboration with NASA. Those with good eyes can probably see the unit here plugged into the laptop. The goal was to monitor the radiation environment inside the station, to monitor the radiation for electronic equipment safety and, of course, the human crew safety of the astronauts. 1 year later, we developed SATRAM device, which was the first use of Timepix in open space, so in vacuum, temperature changes in space, and and also unshielded from radiation. It was launched on board ESA satellite Proba V in 2013, and is, after 9 years, it's still working, providing us with invaluable space heritage. Because, you know, in space, heritage is everything. You can have wonderful wonderful devices, but if they didn't fly yet, I mean, not many people will be interested. Timepix can, apart from radiation, it can also detect high energy photons, X-rays and gamma rays. So it was used as a X-ray sensor in the Vzdušsat-1 Czech satellite, which was launched 5 years ago. Together with VZLU and Faculty of Electrical Engineering. Of course, problem with small CubeSat is a low data rate, low downlink to Earth. So you can compare here. This is over 1.5 years, roughly, that basically in SATRAM we were live for almost a year, so 340 days. While at Vzdušsat we were only able to measure and send data for 11 hours. But you can see the data are similar, showing you know, the regions of high fluxes in polar regions and South Atlantic anomaly. We were also providing 2 detectors for X-ray telescopes on board NASA sounding rocket. I guess René will talk about REX. This was launched in 2018. And our last visit to space was on board Japanese satellite RISASat, for which we developed a detector with 2 Timepix sensors. It was launched in 2019 in collaboration with Tohoku University. So as you can see, majority of Timepix-based radiation sensors were developed at our institute. So there was a bit of history. Now let's see what we do now. We are close to finishing the development of a new generation of detector called HardPix. It's modular design, and it's based on the newest Timepix 3 sensor. You can choose if you want 1 or 2 layers. It's modular in a sense that you can choose also connector. You can choose what type of onboard processing unit you want. So it's equipped for the first time with onboard processing. So even in orbit, it identifies protons, electrons, and ions and provides flux and energy spectra for each type of these particles, together with the total ionizing dose. This is great because it significantly reduces the amount of data needed to be transferred to Earth to few kilobytes a day. So even on small CubeSat, it can be basically running non-stop. The first deployment in space of HardPix will hopefully be next year on board ESA mission GOMEX-5. That's a 12-unit CubeSat. They are testing some electronic propulsion, so they will go up to 1,000 kilometers. And our flagship project now is ERSA. So due to our heritage, HardPix was selected by ESA to be part of their radiation sensors array, which will be externally mounted to Lunar Gateway. That's the orbital station which will orbit around the moon, part of the NASA's Artemis program to return human to moon. So as you can see, so here are two HardPix units, and this whole ERSA element will be externally mounted to the power and propulsion element, which is one of the first or the very first part of the Lunar Gateway. So it will be launched with SpaceX in 2024. Another area of interest, which is connected to the commercial interest of lunar surface or going to the moon, is mapping of the presence of water and other elements on lunar surface. So from orbital imagery, we know that, there is some evidence of water present on lunar poles. And this was mostly done by neutron spectroscopy. So when you have no atmosphere, you have a lot of galactic cosmic rays impacting the surface. They create fast neutrons, and these neutrons are moderated or slowed down by the soil. If there is water, they are moderated more, so they are slowed more. And by these variations of epithermal and thermal neutron flux, you can detect water in the first meter of subsurface without drilling or any other invasive technique. So HardPix, if equipped with a neutron conversion layer, thanks to its miniature size, low mass, low power consumption, low cost, can be placed on board these lunar rovers, even small rovers like Cube rover, which is a small rovers planned by Astrobotic company, to map water presence directly on lunar surface. This was important to have a small device which has low resources requirements. So the same way HardPix can be used as a radiation monitor on any small satellite because it's smaller than 0.1 unit. It has 150 grams and 1.5 watts. It can also be used on any rover because the cost of 1 kilo to lunar surface is now roughly $1.2 million. So it's important to have something small. We are part of ESA project to study possible use of HardPix on European rover. We also study, this is the last thing, we also study PAN, penetrating particle analyzer, which is a magnetic spectrometer for detection of highly energetic particles up to tens of GeV. We are part of European Commission Horizon 2020 project to develop a small demonstrator, MiniPAN, together with universities in Switzerland and Italy. And we also one of these Czech ambitious projects called REMEC, which will have the goal to send MiniPAN and HardPix units to outside of Earth magnetosphere to monitor galactic cosmic rays in deep space. Also, PAN is now being selected for Athena mission as well. So as you can see, our institute is leader. definitely in the Czech Republic in the field of space radiation detectors used for protection of human crew. So either on ISS Gateway, we are even trying to get onto airplanes, but to get aircraft certification is quite difficult. And protection of electronic components, you can monitor online the level of radiation. If it's high, you switch off the whole satellite, keep just HardPix running. When it's low again, you switch on the satellite again. Of course, we are scientists, so we still study space weather and heliophysics. There's the goal of gateway units as well. Prospecting, so using neutron and gamma spectrometers to detect elements on extraterrestrial bodies. And imaging, so if you have X-ray or gamma ray optics, you can use our detectors for imaging of your targets. Well, thank you very much.
So thank you very much for your interesting presentation. Are there any questions?
SATRAM is 820 kilometers SSO, and VZUSAT-1 is also SSO, but 400, 500? 500. No, it's purely ours, yeah. We didn't want to share. Sorry? Yes.
So any other questions? If no, okay.
During the development of the hardware and the software, you have to follow for the ESA mission the standards, right? The ECSS. No.
Yes, I mean, we are developing mainly prototypes, breadboards, and engineering modules. And for flight modules, we use BD sensors or CSRC, how they are called. So they have all the certification for manufacturing and you know, all the PAQA certificates and ISO certificates, which we as university don't care about. So we use companies for flight modules. And hope that if it gets commercialized and mass produced, they will be able to sell it with a license from us. So that's the goal.
So thank you very much for your presentation.